So Anonymous said, do we have to join as a panelist again? It depends. I mean, if you so I don't know who you are, so I don't know if you sent the video form. If you sent me you can private message. Well, you can't private message. I mean, you have to say, yeah, that's great. I need to know your name to know to check our spreadsheet and make sure that you indeed fill out the form. So whenever you feel comfortable, just share that with me and I'll double check. Jumana, you said no one was saying, no, someone was saying, I'm not sure what you're referring to. Would you mind clarifying what you're trying to say? I would appreciate it. So Jumana, maybe you're the anonymous that sent the message before. I don't see your video release form. I'm gonna double check. Oh, I found it. Let me fix that. All right, you should be able to join in just a second. Stelios, let's see. Yep, I see you, Stelios. Just remember when you log in to Zoom to use the same email that you shared with us. So that things are automated, but Esha, yep, Esha, you should be a panelist as well. Okay.
Sir, the process of joining as panelist is automated.
Sorry, I couldn't hear that. Was that Jumana trying to speak?
The process of joining as panelist is automated by email.
Yeah, that's right.
Oh, okay. Actually, I am using a different email for LCM, so I have to.
Jumana, sorry. Would you mind turning off your mic for a second? So it sounds like you have a lot of background noise. It sounds like there's somebody speaking behind you. And so it's very hard.
Sorry, sir. So actually, I have a different email for Zoom. So
that's probably that's probably the issue. So if you're using a different email from Zoom versus the one that you provided us, then it's not gonna be automated. So so we'll be running into this problem over and over again. The easiest thing, since we're using, you registered with an email already, and that's what we have in all of our databases, is for you to use the same emails going forward. And unfortunately, Jumana, you have a lot of background noise. So for us to be able to communicate, maybe either try to figure out what the background noise issue is, or maybe use the chat feature. Okay, I think I'm promoted everybody to a panelist that is supposed to be a panelist. No worries, Jemana. I see that you're not used to Zoom webinar. It takes a little bit, but I think we're all on the same page. Okay, so I think everybody that needed to be promoted has been promoted. And why don't we go ahead and get started? So first, I wanted to do a couple of reminders that folks are supposed to be writing reports about their progress. This is important because the way that at the end of the program, we're going to be giving you certificates of your participation, and we're going to use your progress reports, your weekly progress reports, as a metric of your participation. And so I see that most people have stopped around week 1. So we're going to need you to write one per week. It doesn't take that much time, so please don't forget to do that. And there's no immediate deadline for when it should be done, so you can still catch up. I saw somebody ask, when is the last day to submit the week 4 report? There's no exact date, so the sooner the better. I think we're gonna keep going we're gonna continue the program at least until September, October. So when that date is announced, that will be the last day for you to be able to submit the 4-week reports. We're gonna continue our meetings, but there's no expectation for people to continue doing report beyond week 4, other than if you want to continue on this line of work, then you will have to continue working. So I think that answers that question, which just got posted yet again on the Q&A. Anonymous, was it clear? Is it clear now? By when do you have to submit the report? There's no date set yet, but it's going to be around September, October when the mentoring program ends. That will be announced shortly. Okay. If there's any questions about that, put them on the Q&A or put them on the chat. The other thing that I wanted to say is that we have our weekly meetings, which is this is part of those weekly meetings. But on top of that, we have weekly meetings that are part of the whole mentor program, not just our research project. And the attendance for those has dwindled. It has dropped a little bit. And so I want to strongly encourage everybody to go to those meetings, which take place on Thursdays at 1 p.m. Eastern time. That's a good opportunity for you to talk about your progress with other students from all over the world. It's a lot of fun. It's low pressure. And it's just a way for you to meet people from other parts of the world that are doing similar things. Also, you're able to meet some of the other mentors, and so you might be able to ask them questions. It's a little more intimate, and so I want to encourage everybody to go to those meetings. And so you should have received a reminder of it, I think today or yesterday. So please go to those meetings on Thursdays. Did anybody not receive the reminder of those meetings? Does anybody need me to post the Zoom invitation for that, or the Zoom link for that? Oh, sorry. Yes, it's at noon Eastern time, not 1 p.m. Thanks, Renata. Renata. Okay. If there's nothing else about that, are there any questions about what's been covered so far? Do people have any questions about where, material that has been presented, on things that will be? Yeah, I see Renata raise her hand. Renata, you want to speak?
Yes, I have a question about the exercise that was shown last week about the plotting of the graph.
Yep.
It has to do, sorry, with the way E star is, I don't know, shown, because the range shows a variable as E star divided by M. So I'm guessing we don't have M. Therefore, I have stumbled upon a problem with plotting Q star for the row operator function, phase space. I don't know what to call it.
Okay, sounds good. That's a good question. So I'll do what I like to do a lot of times, which is skip your question and ask somebody else to answer it. Does anybody else want to try to tell Renata what M is supposed to be in these exercises? Kian, do you want to give it a shot?
Well, I took the range as being the ratio E over M and reorganizing the equations so that using the variable as E, the ratio E over M when plotting it, instead of using the number as E.
Yeah, that works too. There's even something simpler that you can do, but that should work. I think maybe Harshit, do you want to?
Yeah, I believe when you can assign a random number for M and it'll cancel out when you do the calculations.
That's also true. Yeah, it should be independent of M at the end of the day. So one very natural choice is to make, as long as M is not 0. So if you divide by 0, then life is going to be really hard because you're going to be dividing by, you're going to get something numerically that is not a number. Just set M equals to 1. And at the end of the day, everything will be independent of your choice in M. So everything is the reason why is because you're doing everything in dimensionless units. So all the quantities that you're plotting they don't care about dimensions. And so the dimensions are set by your choice in M. So if you set it to 1, then everything else, basically at the end of the day, everything is independent of that. Does that resolve things, Renata?
Yeah, I was thinking about something similar, but I wasn't sure whether or not it was correct. So.
Yeah, okay. One way that you can that you can test whether, if you have an intuition and you want to just test it out, the beauty about numerical stuff and even, analytical stuff is just test it out, right? Just pick a choice of M equals to 1, make a plot, right? And then make a choice of M equals to 2 and see what you get. But implicitly what's going on is that we're assuming that M is equal to 1. And I don't remember if Andrew made it very explicit, but if you make it, so something that we can just make a little more clear, but M equals to 1 should work.
So I didn't understand Renata's question actually. The question that was given was E star by M. It was given in a certain range. So M can take any of the values, right? So if suppose is right.
Yep. Just not 0. It has to be a positive number that is not 0.
So if we know the value of E star, say, I don't know, some value, then we can actually find out the mass of the particle using the plot that we have. Is that correct?
Well, the problem is that all you're given is E over M. And you're not given M. So you have to pick a choice for M. And so all I'm saying is that the most natural choice is to set it at 1, which is what we've been assuming in these exercises. I can't remember if Andrew had made that explicit or not. So the answer is, for all intents and purposes, just set it equal to 1, and you should be able to reproduce the plots. Does that make sense?
Yes, it does.
Cool. It sounds like you have like a radio right next to you. Is that right, Jumana? Or you have like people chatting?
Actually, it's my mother talking, and
sounds good. All right. Okay, Renata, you have your hand raised. Does that answer your? Are you okay?
Yeah, that was a mistake. Sorry.
No, it's okay. Kian, you have your hand raised. No, you're good. Okay, Rahul, you have your hand raised.
Yeah, basically, we're assuming that m is mass and that the mass of the particle is equal to 1. Is that right?
Yep.
Okay. I have the second question, which is basically what is whether m is a matrix or complex number, because we have this kind of s-1 formulation where the way I understand it is that the s-1 matrix transforms the incoming wave into the outgoing wave. Like it's a transformation. And so like, do we consider m as a matrix or as a complex number? Yeah.
So m is, so let me share my screen for. So the scattering amplitude, and I'll talk about the scattering amplitude in a complementary way that Andrew has been talking about, using simple Feynman diagrams. So we're going to touch on this today, and perhaps the best thing is, how about why don't we table your question and then come back to it at the end? I think it might be good for me to go step by step and motivating yet again scattering amplitudes, and I'll talk about how you can think about them in the context of Feynman diagrams a little bit. I'm just going to give you a little bit of an intro into Feynman diagrams, and then we can skip forward back to your question. Is that okay?
Sure. Sounds good.
Okay, perfect. Okay. So maybe, unless there's any other immediately pressing questions, why don't I start lecturing on the topic that we're going to be covering today, which is a introduction, a motivation into QCD spectroscopy, and a motivation yet again of scattering amplitudes, and then jumping into Feynman diagrams. So let me just repeat some of the things that you've heard already several times, but it's new, right? It's exotic, and so it bears repeating. The goal that we are trying to achieve in our research is we're trying to understand the theory of quantum chromodynamics, and there's many things that are left to understand about the theory. The simplest thing that we want to assess is, what are the states of the theory? What are their masses? What are their properties? And this falls under the realm of spectroscopy. Spectroscopy of atoms and molecules is a very robust and very well studied field. It dates back over 100 years, while the analogous study in QCD is far more challenging, because the theory is far richer, and there's many outstanding questions. And if you look at the sector, you can look at different sectors in the theory, and I'll show you some examples. So the simplest sector that we can imagine is that where the proton and the neutron lies. Whoop. Let me go back. I don't know what happened. There we go. Where the proton and the neutron lies, and this is generically the proton and neutron are clumped together into a single state, which is called a nucleon, because the protons and neutrons they seem to be so similar. They have a very similar mass. They have the same spin. In the context of nuclear physics, they look very, very much alike, and so they're sometimes clumped together into a some state that is a combination of these, which is the nucleon. If you look at the first excited state of the nucleon, that state is called the Roper. The first excited state of the pion, which is a simple state composed of quark-antiquark pairs, and this is perhaps arguably the simplest state of QCD. Well, its first excited state also has the pion symbol, which is pi, but it has a number associated with it, which is approximately its mass. Both of these states are, in fact, not stable. They decay rapidly into multi states composed of other particles. So they decay into multi-particle states. So the Roper decays to a proton and a pion, or a proton or nucleon, I should say, a nucleon and two pions. This decay can happen in the order of 50 to 70% of the time, while this decay can happen in the order of 25 to 50% of the time. This state decays into three pions via an intermediate decay of a rho and a pi, and then this rho decays to two pions. And so these are states that decay rapidly in orders of 10 to the minus 23 seconds. And because of this, they're thought of as resonance states that live for a very short time and then decay, okay? And so this motivates the idea of studying properties of multi-particle states and trying to reconstruct the intermediate states that can be created, like the pi 1300 and the Roper. And so most of the states of the theory, in fact, over 99% of them are of this nature. Okay, it's very few of them that are in fact stable under the strong interactions. And so what I wanted to do is give you a little bit more taste on this. These are slides that I showed before. Let me zoom out. And I wanted to share some more on this topic. And to do this, I'm going to pull up a website that is very useful. Which is the review of particle physics by the particle data group, where basically the particles that are known to this date are listed and enumerated, okay? And so here I have some notes on the side, but this is a website that is freely available and you can look it up yourself. It's pdg.lbl.gov. And so it's fun to just like basically go in there and see all the different states that exist. And we're gonna do a little tour ourselves, okay? And so this is I have a little screenshot next to it. Let me put them side by side so I don't have to keep scaling my. There we go, perfect. And so this is actually a screenshot of the 2020 particle, the Rio particle physics. This has been updated. So this is a 2021, they update it every year. And so there's an update of this field keeps changing. There's particles that are identified to be, that are discovered all the time and they get confirmed. And so this needs update all the time to be able to say, tell us which particles are indeed present in nature and which ones are just a fluke of nature, a fluke of an experiment, and they end up disappearing. And so there's different types of particles. Some of these should seem familiar by now, right? You have the gauge particles. So this would be the photon, the W and the Z, and gluons, as well as the Higgs. Then you have leptons, which include the leptons includes the electron, muon, tau, neutrinos, heavy leptons, quarks. And you have different properties about the quarks, all the different quarks, and they have some evidence of their experimental evidence of their existence. And what I want to show is the mesonic sector. So this is a very well understood sector. There's a lot of open questions. Perhaps let me zoom out. There's also the baryons, and there's other more exotic stuff. So if you look at the mesonic sector, there's different kinds of mesons. So these are particles that are composed of at least quark and anti-quark pair. So you have a quark and anti-quark, and then you can have more exotic combinations. So they have basically their spin has to be integers. So it can be 0, 1, 2, etc. While baryons, they have integer spin, so their spin can be 1/2, 3/2, 5/2, etc. Okay, so let's zoom in here, and this is the scenario that I considered, and that's what I have in my list on the side. And what I decided to do is just basically do a little summary table of some of the lowest lying states in this list. So you see the pi plus, pi minus, that's up here. The pi 0 is over here. There's the F naught. I have the eta over here. I have the F naught, and then the rho. And you can zoom in into any of these. And what you will see is that if I hit this number, if I hit the pi plus, there we go. You get a bunch of information about them. There's just almost too much information. So you can play around with this and look at it, but at first is an overwhelming amount of information. You have various different properties, categorical properties about them. The first thing that you see is their mass. These are in these funny units that are MeV, and so you can see a determination of the mass from different experimental observations, and then you have a global analysis of what the particle data group suggests is the best determination of the mass, and you see an error. So what is being quoted is the mass plus or minus their uncertainty. And so you can see that the uncertainties are very, very small. These are particles that are very, very well understood. And after that, what else do we see? This is their quote for their best fit. Then you have averages, and here you have the mean lifetime. So there's a lifetime of the particle in units of 10 to the minus 8 seconds. So you see it's approximately 2.6 times 10 to the negative 8 seconds. So this is a very, very short-lived state, right? These things decay very rapidly, but our experiments are so precise and so accurate that you can see that their masses can be determined very well, even though these things can decay rapidly. And in fact, and so what I'm showing you here is basically I just went through these tables one by one, and I just quoted their masses in approximate, I didn't fuss over exact numbers because I don't think it's all that useful unless you're doing precision physics, right? Here, the number that is being quoted is 139.6, basically, although that number, these are significant figures because the uncertainty is so tiny. Well, I didn't quote an error. I just rounded this up to 140, just for simplicity, okay? And so let me now just focus on my table and just ignore a little bit of what's in the PDG. Okay, so what can we learn about these numbers? So we have the pi plus has a mass of approximately 140. It decays rapidly to multiple decays, and you can see here the dominant decay. Oh, wait, I didn't show you the decay mechanisms. Aha, here we go. Here's the other thing that you can learn, which is the decay modes, and that's what I'm quoting here, the decay channels. So it decays, it can decay to all these different ways. So meaning in the rules that are encoded in the standard model particle physics, and consequently what is being reflected in nature, these are the observed decay modes. They can decay to a muon and a neutrino, or a muon neutrino photon. And notice the pi plus, right, has positive charge, right? And one of the things that we know in nature is that charge is conserved. And so whatever it decays to, so in this case, it decays to a mu plus and a neutrino, the total charge of this has to be equal to the charge of the pi plus. And indeed it is, right? The mu plus is positively charged. This is the antiparticle of the muon, and then the neutrino is neutral. And you can see that in all the decays, so for example, here's a more complicated decay where it decays to a positron, neutrino, positron, electron. And you can see that the total charge is, again, just you get one total positive charge. The positron and the electron have equal and opposite charges, so the total charge here is 0. The neutrino is neutral, and the positron is positive, and so the total charge of this decay mode is positive. And you can see that's the case for all of them. So you have a mu plus neutrino, and then you have a neutrino antineutrino pair. And what you can see here is the percentage of the time that it decays to one mode or another. So you can see that this decay is almost 100%, almost 100%, right? This is very, very close to 100, right? While the other contributions, they're not 0, but they're pretty close to 0, right? This is 10 to the minus 4. So this is several orders of magnitude smaller than this. And these are all, you see this gets increasingly small, right? But they still are measured and they're not 0, right? This is several standard deviations away from 0. So that's really remarkable, right? That these things can be studied so to such high precision. So Aditya is asking which flavor of neutrinos do the neutrinos that don't have any subscript denote? That's a good question. I don't actually know. And I mean, it's going to be some combination of electron and muon, neutrino and antineutrino, and they're going to oscillate. So I think that's the point, is that these are not necessarily detected. The neutrino antineutrino pairs are not detected. And what you're seeing here is that, in fact, this is not what they're putting here is an upper bound, right? So these are not decays that have been determined with any precision, and so it's not clear which neutrino or antineutrino would be the ones that are being created. Esha is getting ahead of me. Esha is asking, is there always one channel that dominates or you can have multiple that are equally likely? We're going to get to that. All right, so that's a great question. Now, this thing keeps. All right, so like I said, what I did here is that I pulled up all the lowest lying states, and we can see some of the questions that we just asked. So that was just asked. So okay, let's continue. So we've just been talking about the pi plus this whole time. The pi plus has a partner that looks very much the same. It looks very close to it, but it's neutral. So the pi plus and the pi minus, they both satisfy this property. They have the same mass, the same lifetime, and the only difference is that the decay modes they get flipped in sign. So instead of decaying to a mu plus, mu minus, it decays to a mu minus neutrino. Okay, so that's the only difference. Then the pi 0 is a partner of these two, but it's neutral. Its mass is not quite the same. It's a little bit shifted, but it's very, very close. It has a very, there's something that is telling us that, these masses have to be closely related, and they are, okay? But one thing that is very striking, that is very different, is the lifetimes are very different. So this decays in orders of 10 to the minus 8 seconds, while this decays in the orders 10 to the negative 17 seconds. And I just realized that my color scheme has importance, and I should have pointed this out before. My color scheme is either purple, blue, or red, and what is being denoted is the mechanism through which it decays. Okay, we know that in the subatomic world, there's 3 forces that are at play. The first one is electricity and magnetism, which the underlying theory is QED, quantum electrodynamics. The second one is a weak nuclear force, okay? And then the third one is the strong nuclear force. I see that, and so the color coding corresponds to the different to the different forces that are responsible for the decay mechanism. Wouldn't there be, so I'm seeing Jumana is asking, wouldn't there be a difference in momentum between the first and second reaction for pi plus? If so, then what about momentum conservation? Yeah, momentum is always conserved. So what ends up happening, so the question is, I think it's about this one and this one, right? Is that what you're asking, Jumana?
Yes, sir.
Great. Okay, sounds good. That's a good question. Let's take a little detour. So there's certain things that always get conserved in decay in any reaction. One of them is energy. The other one is momentum conservation. And so in the first decay mechanism, you have the pi plus. The pi plus going to a neutrino, a muon, and a neutrino. Okay, and this decay can happen in any frame where the pion is either moving or in any direction, or it could be static. Okay, let's think about the frame in which is static. It doesn't really matter. The physics is going to be the same, but it's simpler to think about the static frame. Okay, so originally you have the pion, which is not moving, and so it's for momentum, right? The momenta, basically the energy and momentum is going to be, well, the momentum, the spatial component of the momentum is going to be 0 because it's not moving, and then the energy, well, it's going to be just its mass, because Einstein told us that the energy of a particle is equal to its mass squared plus the momentum squared, all square rooted. Okay, and I'm assuming the speed of light is equal to 1. So in the limit that the momentum is equal, the spatial momentum goes to 0, then this is just equal to m squared square rooted, which is just equal to m. Okay, and that's what I did. So let's move this guy over here. And so what we know is that at the end of the day, this is going to decay to a muon with some momentum, and then some neutrino with some momentum. And what has to be the case, oh, I'm saying that I'm screwing up here. Let me just call this. This is going to be confusing. Let me call this 1 pi. Okay. And so what is the case is that the original form momentum, so the energy, what I have is that the energy of the pion, which was equal to its mass, has to be equal to the energy of the muon plus the energy of the neutrino. And on top of that, the original momentum of the pion, which is just equal to 0 in all directions, has to be equal to the momentum of the neutrino, or the muon, sorry, plus the energy, or the momentum of the neutrino. And so this tells me that these two guys have to be going in equal and opposite direction. Okay, so they're just going back to back, which is, what I depict here, right? And then this gives you a constraint also, since these guys are, so this is the mass of the pion over here, mass of the pion, let's not get sloppy. And then you would have that, you would have this condition. Let me move this around because I'm running out of space. So notice I put in that the momentum of the neutrino is equal to the momentum of the muon. I already used that over here. The magnitude is, since I'm taking a square, the sign doesn't matter. So you would have this condition at the end of the day constraining the energy conservation. What happens when you have 3 particle decays is essentially the same. You just have more variables at the end of the day. So you have, in the case of, you have a muon, a photon, and a neutrino. So you have a decay like this, right? They have to go fanned out, and basically you just have the mass of the pion, which is original energy, has to be the energy of the neutrino plus the energy of the photon plus the energy of the muon. And then you have the momentum of the original state, which is 0, has to be equal to the sum of the momenta of the outgoing states. So life gets a little more complicated. You just have more variables and less constraints. Okay, that's all. But you always have momentum and energy conservation. You always have energy momentum conservation. Ash is asking, would there also be some energy mass conservation to play into this? Well, what you have is energy conservation and momentum conservation, and mass is just one example of energy, right? It's just the energy that particles have when they're not moving. Okay. So here, let me move Jazzy. You want to say hi, Jazzy? Hi, everybody. This is Jazzy. All right. Any other questions?
Sir, if we have 3 particles, then wouldn't the energy of the photon be will be taken from one of the particles which are eventually expelled? So wouldn't that mean that there's a difference between the energy of individual particles of the first reaction and the second reaction?
Yeah. So you're saying these guys would be less energetic in this process because the photon is taking some energy. Is that what you're saying?
Yes.
Yeah.
Okay,
you basically, yeah, it has to be the case because the photon has to carry some energy. It has to be that this has to be, and this also has to be equal to let's say the neutrino plus muon energy in the first reaction. So I'm putting here. So if I put a little subscript saying second reaction, right? This has to be these have to be equal, therefore this has to be greater than the sum of these two guys.
And so, okay, what was I going to ask?
I mean, this is interesting, but it's not immediately relevant. I mean, it's I think maybe, I mean, it's not that it's not immediately relevant. It's just so you have this inequality. That's the case for sure.
And so, is that why there is more percentage of the first reaction than the second reaction? Because the energy is equally distributed in the first one between the particles.
No, it's dynamics. This is suppressed because you basically have a weak and electromagnetic decay. So that's a harder thing to explain. For that you need to we would have to learn a little bit about field theory and Feynman diagrams, and so you're going to learn a little bit about it, but it's outside of the scope of this meeting. So but that's a good question. So okay, so let's keep going down, and this is going to give you a sense of a little bit of what I'm trying to say. So maybe just keep this. Maybe this question will get answered after we continue a little bit forward. I saw that Ahmed had his hand raised. Ahmed, did you want to say anything?
Yeah, you are saying that in any decay, the energy is always conserved, right?
Mm-hmm.
So I looked when a proton decays to a neutron, it produces W plus. It has a greater mass than the proton, right? So how is it conserved?
Yeah, so that's a great question. It's hard to explain for a second because what's happening is that you have a neutron, and a neutron, and then this turns into a proton, and you end up having, so the proton is positively charged, right? So you have a neutron that is neutral, it doesn't have charge. The proton is positively charged, and so whatever is being emitted here has to be positively charged, which is a W. The W in this case, because it doesn't have, you don't have enough mass energy for it to become stable. It's in fact, it's not a real particle. It's what is called a virtual particle, and it ends up decaying to a combination that is also positively charged, which is a positron and a neutrino, and so you end up having this decay. This is a neutrino of the electron. The question, so
it's okay for a virtual particle to have a greater mass than the original?
Yeah, but this is not, so that the energy that is flowing through this, so there's if you look in what has to happen is that in every vertex here, so here you have, let's say, the energy that is flowing is equal to the mass of the neutron, okay? Here, this will have some energy, which is the energy of the proton. It's not going to be the mass of the proton. It's going to be moving, okay? So the energy is going to be a little bit greater than the proton. And so what has to flow this way has to be, so the energy that's going to be flowing that way is going to be equal to the original energy minus the energy of the proton, which is going to be less than the mass of the W. In fact, it's going to be much less than the mass of the W. And so that's what I meant. This particle does not have enough energy to actually become a real honest to God particle. And so that's okay. You can create particles that are heavy for a short instance in time due to the uncertainty principle in quantum mechanics. And so you can have states that get created for short instances of time and then you can have them, they ultimately have to decay. They can't
Okay.
live. So they can live for, basically you have that, the product of the energy needed to create, you can create some state that is really heavy by a short instance in time, as long as this is, satisfied by the Heisenberg principle. So it's going to be, what is it, h bar over 2. And so you can have a short-lived state to a heavy state. So this can be a large number, but then this delta t has to be a very, very small value.
Yeah, I got it. Thanks.
All right, that's great then. Okay. All right, these are all great questions. So I think, so we were, okay, so DT was asking, does the W have to be negative? No, the W has a negative and a positive partner. The question, so Purbika is asking whether the energy is the main criteria to determine whether a particle is real or a fluke short-lived state. Partly, it's not completely. You can have states that are short-lived, even though you have enough energy for them. Since mesons have zero net charge, do they undergo strong interactions? It's unclear what you mean, but it seems like this is generating more questions than perhaps we can answer right now. So why don't we put unless the questions are immediately relevant for the little table that I'm trying to cover, why don't we table these questions? Do people have any questions about this table that are clarifying this table, or people
Professor,
have?
I had a question about the previous example.
Yes. Which example?
The example, yeah, in this one, since it's a neutron that's decaying, shouldn't it be a W minus boson to for charge conservation?
Oh, you're absolutely right. Yes. Sorry, that's what you were asking. Yeah. Very good.
Okay,
Sorry.
thank you.
Sorry. Yep. Yeah. So I think it's at times it's very hard to write, speak, and think. And so it's easy to make silly mistakes like that. But absolutely, you're right. The charge, so in each vertex, the charge has to be conserved. And so you can, just like I did, this flow of momentum, right? I could do the flow of charge. So the original charge is 0. I have positive charge going in this way. Let's just label as Q1, right? And so here the charge has to be Q minus, right? And you can see that in this vertex, right? I have Q being equal to -1. Therefore, over here it has to be, the Q has to be 0, which it is for the neutrino. All right. Does that make sense? Sorry for the confusion. Oh, I see that Andrew spoke up. Andrew, you should have just yelled at me. What the? All right, so let's go back up to the table. So the eta, so the pi 0, I just walked through you to this example, right? It decays to 2 photons, and it has a much shorter lifetime, right? This is a much smaller number than this one by 9 orders of magnitude, roughly. If we continue to look at, and so this is already telling you a little bit of what ends up being true, is that the weak interaction, because it's more weak, it's less strongly interacting, and the particles will live longer than if those particles that are similar that would decay via an electromagnetic interaction. So here the pi 0 is composed essentially of a combination of an up quark and its antiparticle. And what ends up happening is that these decay, and in the process, they emit photons, and they have to be photons in opposite directions, right? Because of momentum conservation, right? So they'll go back to back in back-to-back directions. So you have a photon going this way, and you have a photon going on this way. And so this is a electromagnetic process, and because of this, the lifetime is it's much shorter because the electromagnetic force is stronger than the weak nuclear force. All right, now we start getting into more interesting territory, which is the eta. Well, this is now a particle that has it's similar to the pion. It's not quite the same. It has different property, but it's heavier, and it has a lifetime that is comparable to the pi zero. So it's actually also neutral. It's shorter in lifetime, and this ends up starting to be more interesting, because here we see a scenario where it can decay to 2 photons via the electromagnetic force, but it also can decay to 3 pions, different types of pions, via the strong nuclear force. Remember, the green is supposed to be QCD, the strong nuclear force. And these decay mechanisms are comparable, but because you start having the strong nuclear force present, its lifetime starts to get even shorter because it is a stronger reaction. So life starts to get a little more interesting. The next state that is present is called the F0500. Historically, it's been called the sigma. This is about the same mass as the eta, and it decays almost exclusively, almost 100% of the time, to pions. And this is a purely strong decay, meaning it only decays via QCD. And so this, now you see that the lifetime now drops even further by many orders of magnitude. So now we're talking about 10 to the negative 24. The next state is rho, and it decays almost exclusively to pions, and almost 100% of the time to 2 pions, and its lifetime is comparable to that of the sigma. It's a little bit longer lived, but not by much. And so you're starting to see these gaps, right? These jumps, right? If we go from weak nuclear force, things live, somewhat, even though it's a small time, they live for a significant amount. Then if they decay via the electromagnetic force, their lifetimes drop. And once you start going to purely and dominant strong decays, and then these particles live even shorter amount of time. So I see several questions. Why do we have that difference in QED in the weak interaction process, a difference in the lifetimes even when the mass is lesser than the pi plus? I'm not sure what that question is getting at. Andrew, is Andrew on the call? Maybe he can help me decipher that question.
I'm here. I mean, to me, it seems like the question is asking why is the QED and weak interaction processes have different effects, and that's a question that I don't know how to answer, since that's one of the mysteries of physics, is why the strengths of these interactions are the way they are. If that's not what you're asking, maybe you can rephrase the question.
Yeah, I mean, what we do know is that the strong nuclear force is strong. It's the strongest force in nature, and it's stronger than the electromagnetic force. The electromagnetic force, even though it's not that strong, is stronger than the weak force. So what I'm trying to convey is that things that decay via the strong interactions, because it's such a strong force, the probability for that decay to take place increases compared to that of electromagnetic decay mechanisms, which is itself more strong, a lot stronger than the weak nuclear force, right? So the fact that this is called the strong nuclear force and this is a weak nuclear force, the strong and weak are playing an important role in, they mean something physically, right? And this is an example of the consequences of that. Okay, so hopefully that answered the question. So the question of why, so Esha was asking, why does the ADA have 3 different decay mechanisms? There's in fact, there's nothing that rules out the different possible decay mechanisms. So here you're seeing that the pi plus can have multiple decay mechanisms. I just isolated some. Let's go to other particles. So I think, let me see if I had this example. Yeah. So I had some examples here of other particles actually that can decay to multiple states. Oh, so Jemina was asking, what is capital gamma? Gamma is the decay width. I wasn't gonna talk about that. It's inverse. It's basically gamma is just the inverse. It's just all 1 over the lifetime. That's all it is. Okay. So the lifetime has units of time. Gamma has units of energy. Okay. And it's just a useful parameter when you're thinking about the context of when you start to think about scattering amplitudes that describe these decay mechanisms. All right, let me move on. So a lot of times, in particular in our group and many groups around the world, because QCD is the most poorly understood of the 3 theories of the standard model. The standard model being electricity and magnetism, the weak nuclear force, and the strong nuclear force. The strong nuclear force, because it's so strongly interacting mathematically, is the hardest to study. And because of that, it's and also so 2 things happen. One, it's the hardest to study mathematically. Also, the decay mechanisms of these states is very rapid in experiments, so they're harder to resolve experimentally. And because of this, there's more open questions in that sector of the standard model than in the other sectors. And so a lot of us that focus on the dynamics of QCD, we tend to consider a simplified version of the standard model where we can remove the weak and electromagnetic force, and we just consider QCD on its own. And something interesting ends up happening is that a lot of the states that are unstable in nature end up being stable. Well, not a lot, but some of the states that are unstable in nature end up being stable in this simplified version of the standard model. So for example, the pi plus, which decays via this mechanism, well, there is a weak decay, and the pi zero, which decays via an electromagnetic mechanism, both of them end up being stable. And so their lifetimes go out to infinity. Okay, and this actually is also the case for the neutron. So the neutron, its lifetime goes to infinity because it decays via a weak process, as we just covered, where you have yep, no, I got it right. Good. Where you have a proton, electron, neutrino, right? And so that's also not allowed if you turn off these interactions. So you end up having this. Let's make this bigger. So all these things are disallowed in the simplified world, okay? And so you might say, is this too aggressive? Have we removed too much of the standard model dynamics that we can't describe most of the other states. And no, it's not true, because most of the other states that are in the particle data group in the mesonic and baryonic sector, they decay predominantly to QCD states, right? I showed you, I just went basically one by one on the table, right? And I showed you the last two that I showed you, they decay via the strong interaction, and ends up being that all these other states that are here, they all decay predominantly strongly. And you can see, look, just how many states have been observed, right? All these guys decay predominantly strongly, while the first ones are the only ones that are have some important contribution from the electromagnetic and weak force. So Asha has a question. Asha, what's your question?
So I had a related question. So in the same decay, the first one happens because of QED, and the remaining two are governed by QCD. So does this also reflect something about the range at which these interactions occur? Or
you're talking about these guys?
Yes.
So you're asking, so the eta can decay to 2 photons, and it can also decay to 3 pions. And your question is, can you repeat your question?
Since one is governed by the electromagnetic force and the other by the strong force, and both of those forces have different ranges, so do these occur at a sort of different range or something like that?
You think about the range of interactions for this to take place?
Yes.
Yeah. That's a good question. The way you're gonna think about this, I mean, I think that the range of interactions, you're thinking about a physical range, the length scales, right? Like how far away
Yes.
the particles are. Yeah, okay. I don't think that's the most useful picture. So the way you should think about this, right, is you have so this is composed of two quarks that are tied together, two quarks and antiquarks, very much like the pion. And the length scale, so this radius, it's approximately, so R is approximately 10 to the negative 15 meters. So it's in the order of femtometers. And so these are particles that are shoved together in very, very small distances, right? And so the mechanisms that for the electromagnetic force is just simply that these two annihilate with each other and they emit photons, okay? And so that's perfectly reasonable for it to take place at very short distances, like this, right? Basically, they have to essentially touch each other. And so in this, in this configurations, the particle is going to be moving around. There's going to be some probability that they land on the same spot, and so that can happen.
Okay.
These mechanisms of how essentially you basically have to have some sort of production of other particles for them to be able to produce 3 particles going out. That is harder to paint intuitively, because at this point we don't really have a good intuition for how QCD works, because it's such a strongly interacting theory. And so what we can at least assess is understand how, from the guiding rules, how we can reproduce these decay mechanisms, right? And also we know that they're not inconsistent. We see them in experiments, that we know they're not inconsistent with the constraints placed by the theory, but we don't have a good qualitative understanding on how these mechanisms can take place in general.
Okay.
Does that maybe answer your question?
Yes, thank you.
Okay. All right. So this is all to say that if we, here I listed just some of those states, right, that continue to be unstable, but you can see that this little list, even though is long, is actually very short compared to what we see in nature, right? You see all these particles can decay via the strong interaction. And so most of the particles that are seen in nature are in fact different exotic combinations of quarks and gluons that are being combined to form these intermediate states, and then they decay to increasingly complicated combinations of hadronic particles. Okay. So in this, if I turn off the electromagnetic interactions, then you have a bunch of states that are unstable, right? We talked about the eta, we talked about the sigma, which is now known as F naught 500, can decay to 2 pions. We talked about the rho. Then you have things like the W, eta prime. These guys are just over here. Sorry, not W, I meant omega. So you have the omega, eta prime, the F naught 900, A naught 900. And here you start seeing that the dominant decays can be not just two particles. Well, in this case, you can have 3 particle dominant decays. You can also have multiple channels like pi and 2 pions and kk bar, and they can be equal in magnitude. And so there's just tons of different states that are still outstanding to understand theoretically, because they decay to multi particles via the strong interaction. Okay. So is there a connection? So DT is asking, is there a connection between particles with higher masses predominantly decaying through the strong force mechanism? Yes. Yeah. So the thing, so the question is, why do heavier particles, because that's what's happening, right? These are heavier, and you can see their masses are approximately given by the number right next to their label. So the eta prime, for example, has a mass that is approximately 958. The F naught, this F naught has a mass that is approximately 980, 980 MeV, et cetera, et cetera. So the question is, why is the case that the more heavy the particle is, the more likely it is to decay to the strong interaction? That's a great question. So the reason why the pion can't decay, so the pion, what you have to think about is that the lightest particle that the theory had is the pion. And so the pion can't decay to anything else because it's the lightest particle. And so it can't go, just like the electron, for example, it can't decay to anything because it's the lightest particle out there, or well, it's the lightest particle given some quantum numbers, given some constraints. So in QCD, the pion is the lightest particle, so it just can't decay to anything else. And so that's the case for the pion and the pi plus. Okay. The eta, though, has a mass that is greater than 3 pions. And so it has enough energy for it to decay, right? And here this goes back to this question of whether the particle is real or not, right? If you think about the process, right? You have a pion, and a pion, right? And so the energy of the pions has to be, the energy of each one of the pions has to be equal or greater than, so for each pion, the energy has to be equal or greater than its mass, right? For this decay to be physical. And so that's an important constraint. And indeed, if you look at the mass of the eta, well, we had it before. The mass of the eta is 550. And if you multiply this times 3, you're going to get 420 MeV, right? 3 pi. So this number is indeed greater than 3 m pi, and so that decay is possible for this to happen, right? And so what ends up happening is that if you consider the mass of the particles, you have to think about, so for example, let me make a little table. Let me just plot energy. Let me consider, I'm just going to put some numbers here. So this is 2 m pi That's approximately 280, right? So that's a minimum energy that I can give pions. So this is called the threshold energy for 2 pions. Okay. Let me put here 2 kaons. So a kaon and its antiparticle. So if we forget what the kaon mass is, well, look at this table, right? This has strange particles, including the kaon. I'm just going to round things up, okay? Or just round them around. So here we have a mass of 490, right? And so this is approximately 1,000, right? Pretty much. So it's a little below 1,000 by 980, right? Okay. And so, okay, so I have those. Good, good, good. And so let's go back. And I had this little table that was listing the possible decays. And so here we can see that the F0 980, well, the F0 980 has approximately a mass of, sorry, that's the F0 500, sorry, the F0 500. Well, it's going to be above, it's going to be somewhere between these guys, right? And so F0 500, it's going to be somewhere around here, right? The rho has a mass of approximately 770, so it's going to be somewhere around here. Rho 770. And then the F9 980, well, it's going to be pretty much right on top of this. Okay. And so what's happening? Let me make these a little more solid so we can see them a little bit better. Okay. Well, this guy only has enough energy to decay. Let me make this more solid. And this is, again, just a threshold for 2 kaons. Okay. So this guy can only decay to pions. It can only couple to pions because there's no other particles out there that are light enough for it to couple to. The rho, same story. So it can only decay to 2 pions. Right? The F9 980, it's actually, it has enough energy to couple to both kaons and pions. The mechanism for which it can couple to kaons is slightly more complicated, but it can decay to that. Okay. Then if we look at other particles on the list, so let's go back. We don't have to do guessing. Let's see what other ones are there. Oh. Light on flavor mesons. So you see, then you start having things that are in the order of 1020, 100 and 170, et cetera, you have an F0 1370, right? So these guys are starting to get increasingly heavier, right? And in this picture, I even just consider 2 kaons and a meaning I just consider 2 pions and a kaon antikaon. But then I can also have 3 pions, which is going to be somewhere around 3, 4. So it's going to be somewhere around here. It's going to be the 3 pion threshold, right? And you can start producing more and more pions. And you're going to have also around here is going to be the 2 kaon plus a pion threshold, where you can have 3 particle decays involving 2 kaons and a pion. And life just gets more and more complicated. So the heavier the particle is, then there's nothing that rules out a coupling. Well, there's some things that rule out. You have things called quantum numbers that tell you whether it can indeed couple to any of these channels. But just from energy conservation, all these decays are allowed. Okay. So the question is, if the particle has enough energy, will it decay to any of these one channels? The answer is not alone. You have to have things like charge conservation, right? That's an important one. Then there's other quantities like charge that get conserved in these processes. Spin is one of them, on ones that are outside of the scope of this discussion. But there's things that put constraints on that. And sometimes, even though it can couple to these decays, it still may not be, the dynamics may be suppressed for other reasons. And so you don't always have to have those decays possible. All right, I'm realizing that this conversation has been really interesting and it's going very slowly. So perhaps what I'm going to do is finish the motivation of this, and I'm going to save the discussion of Feynman diagrams for next time. So unless Andrew has an objection to that. Is that okay, Andrew?
Yep, fine with me.
Okay, sounds good. All right, so the last things that I'll say is, how do we produce these resonances? So hadronic just refers to bound states of quarks and gluons. Resonances are these short-lived states, these unstable states. That's our name for them. And you've heard these words several times. We know that these can be observed experimentally. So how do we see them experimentally? Well, they can get created in different ways experimentally. It depends on the experimental facility. So here at Jefferson Lab, I'm just giving you 3 examples how these can be created. In particular, the row, which is perhaps the simplest resonant that we have studied. So it's one that is remarkably well studied, and we've done several studies ourselves directly from QCD. So in Jefferson Lab, what we have is an electron beam that gets, and here, this is perhaps the beginning of Feynman diagrams. I'm just gonna give you a qualitative understanding of them at this point. So what we have is the particles are, here is our initial state of particles. You have an electron that is accelerated, you have a proton that is static. The electron comes in and emits a photon. That's a wiggly line. This photon then hits the proton with enough energy that it can not just bounce off at some non-zero momentum, but it's so highly energetic that it can create an intermediate particle, namely the rho. Hey, Jesse. This rho is unstable, so in a short period of time, it's going to have to decay, and it's going to decay to pions, as we already said. It can decay to other things, but the pions is the dominant decay. And so this is how this particle is in study. You can study the energy dependence of this pi system. So there's some energy and momentum that is flowing out. You can study the energy dependence and see the evidence for the rho. Okay. At Compass, so this is an experiment that takes place at CERN in Switzerland. What is being studied, what you have is you have a pion and proton interacting. So the pion is coming in and it's hitting off of the proton with enough energies that you can not just recoil the proton, but again create the same rho that it gets created over here, and this then decays subsequently again to pions. The same decay mechanism. The rho, just like the pion, comes in 3 different types: positively charged, negatively charged, and neutral. Okay, so there's 3 rhos, just like there's 3 pions: positively charged, negatively charged, and neutral. And so in these 2 scenarios, I'm considering just the positive charge. There's an experiment in Beijing, China, called BESS-3, where what is being smashed over there are electrons and positrons they're being smashed against each other. These are, of course, particle and antiparticle, so they can annihilate and create a massive, a highly energetic photon. And then this photon, which is it's a virtual photon, it will then decay. It will then couple to the neutral partner of the row, which will itself then propagate for a short instance and then decay to pions. Okay, and so all these experiments, all these reactions are leading to the same particle, or at least the same family of particles, to live for some short instant, right? Sometime in the order of 10 to the minus 23 seconds. And then they all decay via the same mechanism to pions. And what is being scanned is the momentum in the final state, and you can study these in detectors. And what you can study is, in particular, is the energy in the center of mass frame of this decay process. And by doing counting of the number of events, and you've seen some now examples of this. What you can see is near the road you have a peak-like behavior with some width that is associated with the decay width. So the width of this distribution is associated, the width at the half the peak is associated with decay width, which is inversely proportional to the lifetime. And the location of the peak is roughly corresponding to the mass of the particle. And so this is how you would see these particles experimentally, and this is how they're searched for in all these different facilities. So let me make some closing remarks about resonances. They are universal, meaning they don't depend on how they get created. Okay, so these different experiments all create the same particle, right? Granted that we bundle this row and this row plus and the row 0 into a family, right? They're all creating the same family of particles, independent of the fact that you're using electrons smash against protons, or pions against smash against protons, or particle-antiparticle pairs. They all create the same particle. That's what I mean by the fact that the particles are universal. And their presence may be less or more obvious in different experiments. And this is because the production for coupling to that given particle could be bigger or smaller depending on the reaction. And this is why we need various different experiments around the world searching for the same particles to be able to give us confidence on the existence of these particles. And this is why there's many different experiments taking place all the time, trying to confirm or prove each other wrong. And this is why these tables get increasingly updated, because there's a lot of data coming in all the time, and more sophisticated analysis that gives more confidence. And hopefully by now, I convinced you that most of the states in the theory that we're trying to study are resonances, and resonances necessarily decay to few body states. And so we have to think about few body physics, and that's been the motivation for studying scattering amplitudes. And one last point that I'll make is this is perhaps less relevant, so maybe I'll just delete it, but resonances and bound states are continuously connected. So they're kind of like two sides of the same coin, but that's going to be not immediately relevant for us. So let's just delete that. Okay. So what I'll say last is that I was going to start walking you a little bit through some of the basics of Feynman diagrams. I've already been touching on them. I've been drawing them. And so I figured I would do a little step back and try to get everybody on the same page. Because ultimately, we'd be trying to study is scattering amplitudes. And the simplest way that we can think about scattering amplitudes is in the context of Feynman diagrams. And so what I was going to start doing is just basically giving you some of the Feynman rules and basic building blocks, but I was going to do this in the simplest theory possible, where what I was going to assume is that the particles can either just propagate or they can interact. And I was going to assume a theory where there's only one particle, and that particle can either just travel or interact with particles that are identical to itself. And so that's where I was going to go. But I think this will take longer than just half an hour. And so perhaps what we can do is take a little bit of time to answer questions and see if there's anything that needs clarification. I see that Purbita got kicked off into the sorry, Purbita. I don't know. It's kind of hard for me. Okay. Oh, I guess that got fixed. All right. I see a question. Give me a second. All right, Harshit, you have a question?
Yeah, so in general, what's the reason for why particles have multiple decay channels? So is there a certain reason why they don't have just one decay channel, but like the reason why there's multiple possible?
You cut off a little bit. You said, is there a reason why what is possible?
Multiple decay channels are possible.
Yeah, so it's because essentially quantum mechanics, it's a probabilistic theory. All we can assess is the probability that some reaction will take place. Okay, and so if you have, let's look at one example. I mean, let's just think about the F9980. That's an interestingly enough one. Okay, so let me zoom into the F9980. So the F9980 is just around the kaon anti-kaon threshold, and it's far above the pi threshold. Okay, and so this means that it has enough energies for it to decay to 2 kaons as well as 2 pions. Okay, and so what ends up happening is that if you carry out your experiment, let's say that here's my experiment. I just put the F naught by itself, right? And I wait for it to decay. Okay. And I see it decay once and decay to 2 pions. Okay. So this is my experiment number 1. Precise. So I just did that. I did my experiment. I waited for it. I prepared the little particle, right? And I wait for it to decay and decay that time to 2 pions, right? And then I did my experiment again. So I'm just going to repeat my experiment. And then it happened again. And, what we know is that roughly this will decay 50-50% of the time to both, right? So that's what we know just empirically, is that it's in the order of 50-50. And so what ends up happening is that you set up the experiment again, and then, hey, it decayed to 2 pions again. That's okay, right? I flipped a coin and I got heads twice. Possible, right? There's nothing that is crazy about that. Then you do it again. Hey, you got 3 heads. That can happen. 4th time, now things change. Then you got 2 cans. Right? And then, the 5th time, you got 2 pions again. And you keep repeating, and then you got a streak. You get a streak of 3 cans. Or let's say 2 cans. And you repeat it, right? And each time I'm going through the process of just creating the F9980 over and over and over again. And you're just counting the number of times that each one of these events happens. And that's essentially what we're comparing, right? Is the predictive probability of these processes to take place versus what we see in nature. And in nature, you're essentially just setting conditions to be roughly the same with the same energy to create these particles. And then you're seeing which ways that, how they decay, what particles they can decay to. And the more times you see it, the more precision you can assess its decay probabilities to all these channels. But if there's nothing that prohibits, right, there could be something that says that this decay is just simply not allowed, right? There could be some, but there has to be some rule in the theory. And there's no rule in the theory that prohibits that. So it just is allowed. So it ends up happening that if you have enough energy and there's nothing that prohibits that decay, then there's going to be some probability that it will happen. That probability could be, high, could be 50%, or it could be very, very low, right? And we saw this in the context of the pi plus. So the pi plus decays to, what do you say, mu and neutrino, right? But it can also decay to a muon neutrino photon, right? But this dominates, right? There's nothing saying this can't happen. But the problem is that this process, what ends up happening is that this is just purely a weak interaction, right? While this is a weak plus QED. And so the QED part makes it even more suppressed because there has to be some weak mechanism, right? There has to be you have to have a weak mechanism for this to happen, but then on top of that, you have to have a electromagnetic interaction for the photon to then decay, or to the photon to be created. And so this is further suppressed because you have to have two different types of intermediate reactions taking place for it to happen. And so the probability of that happening is lower. Is that?
Yeah, so I guess I think you're thinking it's more theoretical sense, but for the F980, I assume that for each of the two decay channels, the conditions necessary are different.
Yeah, they're different because the gap between this to the KK bar is smaller, so the K on anti-K is smaller than this one. It just go ahead.
So basically, is the presence of this certain conditions just completely random? Is there any reason as to why the probability is the way it is?
You're getting at the questions that we're trying to answer. So there's different suggestions of this. Why does it have such a strong coupling to can and anti-can, even though it has, favorably, right? It's more favorable for it to decay naively, for it to decay to two pions that would be highly energetic, right? Basically, the further you are away from that threshold, the more ways that it can decay, and so it's more favorable for it to decay to that state. But even though this has very little energy opening, and in fact, it can even decay, it can even couple to it if it's below it. And so this has suggested that people to say that this state, it's unlike many other states in the sense that it's a molecular combination of a can. It looks like an atomic molecule of a can and an anti-can state. So some people have suggested that this is a very unique type kind of state, and there's in fact various different molecular candidates out there. Meaning it doesn't look like a quark anti-quark pair. Instead, it looks like a quark anti-quark followed by another quark anti-quark that are tied together via the strong interaction. So it looks kind of like the deuteron, which is the lightest atomic nucleus, which is composed of a proton and a neutron. So people have suggested this. Other people have suggested that this is in fact not a molecular type state, but in fact is a quark, is a tetraquark, meaning you have two quarks and two antiquarks that are very close together that has very strong coupling, dynamical coupling to a cation and an antication. So these are open questions. We still haven't, in fact, Andrew and I are working on trying to devise a theoretical framework to be able to say what is more likely, if this kind of picture or just a simple kind of this kind of picture. We're trying to figure out a way that we can study the structure and the shape and the size of these states. And so that's a very interesting question, and it's still outstanding. Yeah, very nice question, Harshit. Yes, so I'm seeing a big shit asking about the ratios of the partial decay width to a total decay width. So unfortunately, I'm not sure I totally understand the question, but I also it's a little, I mean, it's a little technical. So maybe I will spare, I think that maybe, I mean, what is being quoted is the partial decay width to a given channel. And I didn't want to jump into decay width at this point. So I'm gonna say that perhaps that's outside of the scope of this conversation. So maybe we can table this for another time. Is that okay? And I see another panelist issue. So let me move Christina over. So just to remind folks, the problem is that perhaps, and it seems like this is happening with other people, that the email that you sent us that you registered with is not the same email that you're using in Zoom. And so it's hard for us to automate your promotion to a panelist in these sessions unless you give us the email that you're using for Zoom. Okay, maybe if there's not immediate questions related to the content that we covered, what I'll do is remind folks that tomorrow we're going to have another session of the mentor program, where it's going to be less focus on this project and more focus on just trying to discuss with other people about your progress and other people's progress. And so I encourage you to all participate. It's going to be at noon Eastern time. So please come to that. Last time the attendance was a little bit low. And we want to make sure to keep the attendance vibrant. Those meetings are just supposed to be fun, and they're meant for you to be able to just meet people from around the world that have similar interests to you. So, and also possibly meet some of the other mentors. So I think it's a very worthwhile experience. So please come to those. I see that somebody, sorry, Adriana, she asked whether there's exercises regarding today's meeting. No, I figured you have plenty on your plate doing Andrew's exercises, and I'm sure he would be happy to assign even more exercises. So what I'm going to do is just ask you all to catch up on your exercises that Andrew has already presented, and then also don't forget, I mean, basically everybody has to be writing progress reports. I see that people haven't been, the average participant hasn't filed 4 progress reports so far, and you're supposed to have 1 per week. Well, I guess it's the 4th week, so at least you should have 3. So I'm just going to give you time to catch up on Andrew's assignments and for you to write your progress reports. Okay. All right. Is there any other last minute questions before we call it a day? At least until tomorrow, or where we all will meet again, right? Yeah, Rahul. Is the H silent? Is your name pronounced just like mine, Rahul, or is it Rahul?
It's Rahul. The H is pronounced.
Okay, sounds good.
Yeah, I just wanted to remind you of the previous question, like is M a matrix or complex number?
Oh, yeah, okay, yeah. Oh man, I did tell you to remind me. Here, I thought that I was like free for the day. Jeez. Maybe. Okay, I'll give you a quick one, and then we can like touch back on this later. Okay. So the scattering amplitude, so M, is a matrix. So M is a matrix. It's a matrix in the degrees of freedom of the theory, and the simplest one is, I'll say some technical stuff, and then we can try to clarify it, is the angular momentum that the particles can have. And so these can, basically you have a degree of freedom, which is the angle in which these particles can decay, right? And this can be projected into a quantum number, so a property. So basically you have angular momentum, just like you have angular momentum in classical mechanics, right? You have an angular momentum in quantum mechanics. That angular momentum, unlike in classical mechanics, that one is quantized, meaning it can only take some discrete values, and it can only take those discrete values are enumerated from 0 to 1 all the way to infinity in discrete steps. Okay. On top of that, there's another, there's yet another degree of freedom that is related to this, but I'm going to skip over that one. But essentially, the scattering amplitude, one example in which, in the sense that this can be a matrix, is in this enumeration of possible angular momentums, and it ends up being a diagonal matrix in this sense. So you can have L equals 1, and these themselves can be themselves matrices, and I'm just gonna gloss over that detail. Okay, so they can just be matrices in this sense. Okay, and so what we've been considering is the simplest, the first component of this matrix. So this is a complex number, just a simple complex number. Okay, the other way in which it can be a matrix. So okay, so that's one way it can be in which it is a matrix. Okay, the other way in which it can be a matrix is if you consider the energy. So now let me draw energy sideways, because it's typically how we draw it. And I'm gonna put the thresholds associated with 2 pions. Okay, so there's a minimum energy I can give 2 pions, and then 2 cans. Okay, so in this region, let me make this some color, right? In this region, well, I can have pions, right? And they can go to pions. Okay, so that reaction is allowed. Okay, in this region, right, I have enough energy to create not just pions but also kaons, and so life gets more interesting. I can have now pions going to, so let me keep the one above. So now what's going to happen is that I'm going to have a matrix in the possible channels that are open. So I can have, let me just draw them all, and then I'll say what the lines mean. So I can have kaons going to kaons, and then I can have pions going into chaos. And then I can have chaos going to pions. If the theory is invariant under whether the time is flowing forward or backwards, meaning the reaction is the same, would happen with the same probability if time is going forward and backwards, right? Then running the movie this way would be equal to running the movie this way, which is the same, which means that this thing and this thing are equal to each other. Okay. And so in that sense, then the scattering amplitude is a symmetric matrix in channel space. And by channel, I just mean, which are the final and initial states. That's all I mean. So okay. So in that sense, it can also be a matrix. And so the scattering amplitude in general is a matrix, and it's a matrix on the degrees of freedom. In the first case, I was thinking about angular momentum. And there you can have spin is also an example of angular momentum. And so if the particles carry spin, life gets more complicated. But it can also be a matrix in the number of channels that are open. Okay. Does that answer your question?
No. Thank you.
Cool. So Prabit is asking if we're looking at an eigenvalue problem. So we know how these matrices are. So diagonalizing these matrices in angular momentum space is straightforward. And so we can diagonalize them. That's what angular momentum does for you. And it's because it's a conserved quantity in all reactions. So any quantity that is conserved will lead to will allow you to figure out how to diagonalize the amplitude in that space. So in that sense, yeah, it's an eigenvalue problem that we know how to solve effectively. Then the question is, what do the values take for each one of these components? DT is asking, how do we encode information of such reactions in a matrix? Haha, that's outside of the scope of this as well. You guys are asking a lot of really good questions. So parameterizing these kinds of matrices is much harder than just parameterizing this single component. We won't touch on that. If you're really interested about this, there's a lot more to cover. And so we're happy to keep working with some folks on this topic. I think I saw a hand raised and maybe got lowered. But I think maybe it's a good time. We're close to 2 hours, and Andrew and I have to jump off to another meeting. So I'm gonna have to say goodbye to you for today. I'll be available tomorrow again at noon to meet with you guys. So if you guys want to come and chit chat and just have a more casual meeting, please do so. It's only fun if people show up. So come join us. And yeah, it's been really nice getting to talk to you, and we'll see each other tomorrow, if not next week. Okay. All right. I'm going to stop sharing. Hope everybody's doing safe at home and everybody's doing okay. And we'll see each other later. Take care.